Hello, everybody. You guys ready to get started? My name's Dan Reed. I'm a gameplay engineer at Blizzard Entertainment, and today we'll be talking about networking scripted weapons and abilities in Overwatch. Just as a quick reminder, please silence your phones, and if you have any feedback afterwards, please fill out one of the sheets on your way out. So, as a quick introduction, my primary contributions to Overwatch include our scripting system, which I'll be talking about today, as well as projectiles and game modes. I've also assisted with specific weapons and abilities, movement, our spectator mode, and UI, as well as some other things I'm probably forgetting. So for a quick overview, Overwatch implements its high-level logic, including weapon and ability logic, in script using a proprietary scripting system called StateScript. What this talk is about is the why, what, and how of StateScript, why we decided on this particular method of gameplay implementation, what it is exactly, and a bit about how it works under the hood. The networking requirements and solutions, the constraints we had in getting StateScript to work over the internet and the solutions we came up with, and then the benefits and challenges of this approach. What this talk is not about is projectiles, hit registration, and tech for specific abilities. These are all fascinating topics deserving of their own lectures, but they're outside the scope of what we're talking about today. So why StateScript? Well, we needed a way for non-programmers to create high-level logic. We knew we would need to create lots of content, and we didn't want to require an engineer to hand code a solution every time. We wanted a solution that defined game state rather than just reacted to it. A common scripting paradigm is to have a rather opaque game simulation that scripts can react to via events and then sort of nudge in the right direction by setting variables and calling functions, the results of which disappear back into the black box. We saw a need for a more formalized, explicit approach that gave full control of states and state transitions directly to the scripter. We wanted to encourage modular code reuse as much as possible. That is, instead of tackling a feature request as a single vertical stack of functionality, think about the building blocks you would need to make the feature instead, and then make those building blocks. We wanted a painless, reliable way to implement and synchronize state machines. Doing it by hand in code is time-consuming and error-prone, so make the computer do it for you. And we needed something that worked with the rest of our engine. We considered various third-party scripting solutions, but ultimately decided that we'd get the best results by implementing a language that was tightly integrated with our gameplay and engine layers. So what is StateScript? StateScript is a visual scripting language. Each script is a graph of interconnected nodes describing a chunk of gameplay functionality. So some examples of scripts: Tracer's recall ability, the buff you receive when a friendly Lucio is nearby, and the common UI elements that all heroes have. When a script is played, it creates a runtime object known as a StateScript instance. An instance is owned by an entity, such as a hero. If you attended Tim Ford's talk just now, then you'll know all about entities. Instances can be added and removed from entities dynamically. For example, whenever you get stunned, say by a McCree flashbang, an instance of a script that keeps you from moving and aiming is played on you for just a moment before being removed. Multiple instances of the same script are allowed on a single entity. So let's talk about StateScript nodes. First, we have the entry. Entries are the starting point for script execution. This basic one just sends a pulse on its output as soon as the script begins. There are a handful of other types that will wait for a specific message before pulsing. Then we have the conditions. Conditions affect the flow of script execution. This bool condition here just pulses its true or false plug based on some expression. We have actions. Actions are essentially C++ function calls that do some immediate work before pulsing their output plug. This setvar action is by far the most common we have in use. And then we have states. States represent some ongoing work. A state is inactive until it receives a pulse on its begin plug, at which point it activates. The state will then remain active until either it decides to self-deactivate or it's deactivated due to external causes. Under the hood, each state type is a C++ class with a bunch of virtual functions for what to do on activate, on deactivate, on tick, on dependency change, etc. The important part is that they represent behavior that lasts for some amount of time before stopping. This wait state is just about as simple as it gets. As you can see, it will wait for 3 seconds before finishing. Let's talk about variables. StateScript provides bags of variables for storing values. Each instance has its own bag of variables. The owner entity also has a bag of shared variables. In this screenshot, the ammo and clip variable running on Tracer's pulse pistol script is specific to that script, and the ability lock variable is shared by all instances running on the Tracer hero entity. A variable can either be a single primitive value or an array of primitive values. So we found this to be good enough for most purposes, but on at least a few occasions, we've wished that we'd implemented proper support for nested structs and bags. Perhaps we'll get to it someday. Variables can be state-defined, such that their current value is determined by a state script state. So basically, the stored value of a variable can simply be ask this state. Let's talk about properties. State script node behavior is defined by properties. The scripter chooses from a list of config vars to define the value of each property, as you can see here on the right. Config vars may contain nested properties. For example, the get entity head position config var that you can see up top here has a nested property that lets you pick another config var to specify which entity you want the head position of, in this case, the owner of the script. Each config var type is implemented in C++ by a function that provides a value back to the script. So some examples of config vars, we have literals, variables, utilities, which again are basically just C++ accessor functions, and then expressions. So expressions, in addition to being able to do boring things like is foo greater than 3, can reference an optional list of nested config vars, allowing you to say things like, is the distance between get entity position of source and get entity position of target greater than 3? So there are many other state script features that I won't have time to talk about today, but a few are worth mentioning. The first, subgraphs. So each state has a subgraph output plug that pulses whenever it activates. When it deactivates, any states that are part of the subgraph are deactivated as well. Some states have other types of subgraph plugs that activate and deactivate subgraphs at specific times. The Boolean switch state, shown here, is the most common example, with true and false subgraphs that are active whenever a condition is met or not met. So then there are containers. These come in several varieties. The basic kind with a gray border is merely organizational and doesn't affect behavior. The red border containers define which states are part of a subgraph, since otherwise subgraphs are assumed to only go one state deep. The blue ones are client only, and the purple ones are server only, allowing for divergent behavior between server and client when needed. So before we get to our first script example, I want to talk briefly about two important themes in state script. First, lifetime guarantees. In short, states clean up after themselves. When a state deactivates, its logical behavior is finished, so it stops any animations it needs to, clears any effects it owns, resets any variables it's modifying, shuts off any subgraphs it started, and so on. When an instance is removed, it deactivates all its states. When an entity is destroyed, it removes all its instances. And when the game shuts down, it deletes all its entities. This might seem like obvious stuff, but there's an entire class of bugs that scripters don't have to worry about because the contract of every state is that it will implement its onDeactivate call if needed in order to clean up after itself. The other theme is logic style. So state script supports both imperative scripting, do this, then check this, then do this, and declarative scripting. Whenever this is the case, then this should be the case. In part because of the aforementioned lifetime guarantees, we found the declarative style to be the most sane choice for modeling large, complicated features. But the imperative style has its place too, often towards the leaves of these declarative trees. And this brings us to our first script example. So Reaper doesn't have anything on his secondary fire button, so let's give him a new ability. So here's how it will work. The player holds down secondary fire for 1 second. The camera will go into third person, indicating that his ability is now charged up. And then the player releases secondary fire, sending Reaper launching into the air. Note that if the player holds secondary fire for less than 1 second, nothing happens. So let's create the ability in the editor. First, we'll add an entry, so the script gets going right away when Reaper spawns in. Then we'll add a logical button state that executes one subgraph while secondary fire is held, and the other when it's not held. When it is held, wait for 1 second. We'll set ready to launch to true, and then go into third person. So we'll stay this way until secondary fire is released. Note that this video is sped up to roughly double speed. I can't actually work this fast. Once the button is released, we'll check to see if ready to launch is true. It will be if we held the button long enough. And if we did, we'll launch ourselves high into the air. Before then setting ready to launch back to false. If I could type it. Right, there we go. So, as you can see, this script mixes a more declarative style, that is, this behavior should be active while and only while this button is held, with a more imperative style. Wait for 1 second, set ready to launch to true, go into third person. So here we see the new ability being tested. Secondary fire goes down, a second passes, ready to launch goes to true, and we go into third person. Secondary fire goes up, we launch into the air, ready to launch goes back to false. Here we just spam the button and nothing happens. We have to hold it down for at least a second before we become ready to launch and go into third person. So here's a much more complex script. This is Tracer's pulse pistols. I don't have time to go into detail about how it functions, but you can probably spot some of the same principles at work. Declarative scripting, while this is true, then these things should be happening. And imperative scripting, do these things, wait for a second, then do these other things. So before I jump into the networking portion of the talk, I can spare about 5 minutes here or so to give a quick overview of how StateScript is implemented in C++. So there's the core runtime. Timing in Overwatch is based on integer command frames. So of course, StateScript makes use of these too. Each one is 16 milliseconds, giving us just over 60 command frames a second. Entities capable of playing scripts require a StateScript component. For those of you who missed Tim Ford's talk, entities in Overwatch are formed from a series of components that enable systems to perform certain operations on them. This is the Entity Component System model, or ECS for short. A StateScript component contains all the data needed to execute scripts on an entity. So let's go over that data a little bit. There's the internal command frame. On the client, the internal command frame can differ from the rest of the simulation's current command frame while reconciling data from the server. More on that later. We have an array of StateScript instances. We have a bag of owner variables. And then we have the sync manager. I'll be getting into the sync manager in a bit. And then for each StateScript instance, StateScript instances are allocated dynamically as scripts start and stop. Each one has an instance ID, which is important for network serialization. It has a stew graph, which is our asset. This is a pointer to the asset that defines this particular script. Note that this is static data. Nothing in this stew graph object changes during runtime. We have an array of StateScript states. States are polymorphic. They're newed up via a factory when they're first encountered in script and then exist until the script is destroyed. We have a list of future events. These are scheduled pieces of work to perform on states or the instance itself. Events will often get dispatched on the same command frame they were enqueued, though sometimes they're scheduled for the future, such as when dealing with waits. And then we have a bag of instance variables on every instance. By the way, this is a gross simplification of the data. There's a lot more that goes into running StateScript, particularly several flags and cached lists to help improve performance. But these here are the important pieces of data that will be relevant to the rest of the talk. So let's talk about states. The StateScript state base class provides some utility functions, such as for accessing property data, scheduling events, and registering for ticking. The base class also provides some virtual functions for derived classes to implement. So we have onActivate, onDeactivate, onTimer event, onFrameTick, optionally called once per command frame if a state registers for ticking. getStateDefinedValue. This function allows a state to provide an on-demand value for a particular variable. OnInternalDependencyChanged, which I'll discuss next. And then these last three exist to hide some of the turbulence caused by networking. I'll be getting to those later. All states have a StateScript dependency listener, which is an array of pointers to StateScript dependency providers. In turn, each provider is an array of pointers back to listeners, forming a many-to-many relationship. Providers can live on StateScript variables as well as objects outside of StateScript that a state might depend on. The listener is populated lazily at runtime as properties that require certain providers are evaluated. So if a property asked for some entity's health, the state's listener would gain a pointer to a provider on the entity's health component, which would then point back to the listener. When a provider changes, it will call onInternalDependencyChanged on any listening states. This is an important optimization since it means that states don't need to poll to see when values change. They'll be notified. Variables. StateScript var bags contain a table of pointers to StateScript vars, which are allocated when first referenced. The key of each variable is a 16-bit identifier mapping to a registered asset in our asset system. The StateScript var objects can be one of two types. They can be either primitives or primitive arrays. Each primitive is stored using a 128-bit union type capable of storing integers, vectors, pointers to strings, etc. Statescript vars are dependency providers that will notify states of any changes. Statescript vars optionally reference a statescript state to query to obtain their current value. So if you ask the variable for its value, it would just call getStateDefinedValue on the referenced state. The most common use for this is the chase var state, which takes a variable and changes it over time. Before continuing, let's take a brief moment to talk about structured data. So many of the assets in Overwatch are defined using a format we call structured data, or STU for short. We have a compile step that takes these .stu files and generates code to be consumed by our editor, our asset compiler, and our runtime. It's possible to add attributes to and reflect over class types and data members. These attributes are useful to both the Statescript editor as well as the Statescript asset compiler, as I'll be covering a bit later. So now we can talk about the wait states data schema. In this example, we have the structured data definition of our wait Statescript state. As a quick reminder, this isn't C++. Rather, it's the STU markup, which is used to generate the classes describing this data object. Looking at the first member of this STU class, we can see that it only has one property, the timeout duration when this wait state will finish. The constraint attribute above it tells the editor to limit the dropdown of config var options for this property to those config vars that can provide a numeric result, that is, an integer or a float. We also add two plugs at the bottom, one to fire when the state is canceled prematurely, and one to fire when the wait completes. And here is the C++ runtime for the wait state. As you can see, it inherits from the base Statescript state class. This macro at the top helps set up some runtime type information, and then the bulk of the class is here in onActivate. First, we grab a pointer to the STU object containing the data for this state filled out in the editor. This is the object whose class we defined on the previous slide. Then we call getFloat and pass in the timeout config var. This gives us the time in seconds, which we then pass into enqueue finish state event. After that amount of time, the state will fire on its finish plug and then deactivate. Next, we have macros to make sure our abort and finish plugs fire at the expected times. Finally, the macro down at the bottom links up the runtime type with the structured data type, so the Statescript system knows what class to new up when it reaches that point in the script. So I don't have any examples for how actions, conditions, or config vars are implemented, but you can sort of imagine them as much simpler versions of states. They each just have a single function that's invoked. They're made even simpler by the fact that their runtime versions contain no data, so there's nothing to instantiate when they're reached in the script. So that's Statescript in a nutshell. Now we have to figure out how to make a networked game with it. So our first requirement is usability. It must be non-invasive to the scripter, abstracting away any networking details unless absolutely needed. So early on, we decided that we didn't want to require separate server and client scripts. The fear was that even conceptually simple behaviors would require a lot of extra scripting to sync data, and it would be tedious, error-prone scripting at that. So our gameplay team has always had a low tolerance for any work that we think the computer should be doing for us, so it was natural for us to apply this principle to Statescript networking as well. The result is that we run the same script on server and client. We concluded that we could always provide a way for scripters to separate behavior if and when they needed, but that doing so would be opt-in and hopefully rare. Responsiveness. It must accommodate responsive gameplay, meaning player actions should have an immediate effect on the client regardless of latency. So not much to say about this one other than that it would feel really sluggish if you had to wait for a server round trip before getting that visceral feedback that you'd fired a shot or used an ability or started sprinting, etc. Security. It must be secure, preventing hackers from influencing server behavior by sending malicious data. No one likes cheaters. Efficiency. It must be efficient, allowing the game to function on lower quality networks. So Overwatch needs to be able to run on networks all over the world, and sometimes that means having to deal with high latency and dropped packets. Seamlessness. It must be seamless, minimizing noticeable side effects from networking. Initially, we just thought of this as a sort of fix-it-as-you-go problem, but as we implemented more and more node types, it became clear that we needed a formalized way of dealing with some of the unsightly pops and stutters that we were seeing when certain weapons and abilities were used. So now we'll talk about how we fulfilled some of these requirements. First, let's examine what it means for a particular Statescript instance to be synchronized. With synchronized instances, the server and client logically describe the same instance. That is, networking details aside, one could reasonably talk about a single logical instance that both the server and client are simulating. Synchronization is eventually consistent. So no matter what predictions the client makes, no matter what network anomalies transpire, the server and client will eventually get back in sync with each other. And then there are the unsynchronized instances. These instances can still receive messages from and read variables off of synchronized instances, but their internal logic is otherwise independent. So here are some examples of scripts that are played synchronized and unsynchronized. For synchronized instances, we have weapons, abilities, emotes, game modes, map entities such as doors, health packs, etc. And then for unsynchronized instances, we have menus, our hero gallery, the end of match flow, and music. So again, since StageScript has functionality for sending messages between instances, even from synchronized to unsynchronized instances, it's possible to do things like have the game mode scripts instruct the music script to play different music. So one final definition before we dive deep on networking. On a given client, a single networked entity is allowed to be controlled by the player directly. For example, you might be controlling a tracer or a Genji, etc. We refer to this entity and its StageScript instances as being local on that client. All other networked entities and their StageScript instances are remote on that client. Note that there doesn't have to be a local entity. For example, in the context of a kill cam or a play of the game, nothing is being controlled by the player, so there is no local entity. You're just watching what already happened. The server keeps track of which entities are local to which clients. So let's start by talking about server authority. StageScript networking is server authoritative. This means that the server has the final say in what happens. Communication is mostly one way, from server to client. The only gameplay information that travels client to server is button input and aim. I'll touch briefly on how this client to server input works. If you went to Tim's talk before, then you've already heard about this in more detail. Note that the horizontal axis here is real world time. So first, the server sends down an update from the latest command frame that it has simulated. In this example, that's command frame 100. The client receives it and realizes that in order for it to have a say in what happens on the server, its input needs to arrive to the server in time for the server to use it. This means that it can't just send back input for command frame 100 since that has already passed on the server. Instead, it needs to send input for some time in the future. But how far in the future? Well, the server and client enter into a feedback loop where the server analyzes how early or late command frames are arriving and then notifies the client of this measured round trip time, or RTT for short. So if the client sends up input for the command frame corresponding to 100 plus RTT, which in this example is 105, then it should arrive in time for the server to process it. In practice, we actually go a little further into the future based on network conditions. For example, if your RTT varies significantly, we compensate by going a bit further into the future to make sure our input arrives on time. We'll return to the client in a bit, but now that we know how the server gets its input from the client, we can go into detail about the server's synchronization responsibilities. As a quick overview, we first gather input from the clients for the current command frame. We then simulate the current command frame for all entities. As changes occur, store them in StageScript deltas, and then send the deltas to the client. So let's talk about StageScript deltas. If you'll recall from earlier, a StageScript component has a sync manager that keeps its entity in sync between server and client. On the server, this sync manager keeps track of an array of StageScript deltas, which represent the changes that an entity underwent on a particular command frame. Note that we only create these delta objects on frames where something changed. This ends up being a small percentage of frames, since most of the time nothing is changing for a given entity. So let's go over the StageScript delta structure. First, we have the command frame. Note that the StageScript delta represents what changed about an entity between the beginning and end of this command frame. We have an array of all synchronized instances that changed. And then for each member of this array, we have the instance ID, flags for creation and destruction, an array of all instance variables that changed, and for each of those we have the identifier, and for arrays we have the affected index range. By tracking the affected index range, we can avoid having to transmit the entire array. We have an array of indices of states that changed, and another one of indices of actions that executed. Finally, we have an array of all the owner variables that changed on a given command frame. A StageScript delta is stored until all clients have acknowledged receipt of its command frame, at which point it's no longer needed and can be safely deleted. So now we know what changed, but what exactly should we send and to whom? That's where the statescript ghost comes in. A statescript ghost keeps track of what a particular client knows about a particular entity on the server. So let's go over this structure. Statescript ghost has a client ID. It has a command frame that was last acknowledged. We've verified that the client has all the information from this command frame and before. We have an array of pointers to outstanding statescript packets. By outstanding here, I mean that we've transmitted the packet but haven't heard back about it yet, either positively or negatively. Note the underlying network layer in Overwatch will notify individual systems, such as the statescript system, when a packet is acknowledged by the client, or if enough time has passed that it has assumed a negative acknowledgement, or NAC for short, meaning the packet may not have arrived. We take advantage of this feature to maintain the statescript ghost object. Once we get an ACK or a NAC for a packet, we remove it from the outstanding packet list. A statescript ghost exists until its client disconnects. So let's go over the packet. A statescript packet has a local remote flag. Packet payloads are formatted differently based on whether the entity involved is local on the recipient client or not. More on that in a bit. It has a command frame range, start and end. It has a payload to transmit. To build one of these payloads, we first create a union of all statescript deltas in the command frame range. I'm using union here in the mathematical sense. Basically, we just need to know everything that changed in the command frame range. We then serialize the current values of the objects referenced by this union. If the command frame range starts at 0, which it would for a newly connected client, then just send the current value of all objects. We call this a full update. We don't bother with statescript deltas in this case. Statescript packets are stored after transmission and reused whenever the requested command frame range and local remote flag are the same. This is an optimization so we don't spend time rebuilding the exact same payload. And then, similar to the way statescript deltas work, a statescript packet is stored until all clients have acknowledged receipt of its end command frame. So as a quick recap, statescript deltas keep track of what has recently changed on an entity. Statescript ghosts keep track of which statescript deltas each client still needs to know about. And statescript packets are reusable payloads of client-bound data corresponding to one or more statescript deltas. So let's take a quick look at an example of some network traffic regarding a specific entity. On the top timeline here, you see two distinct deltas. These correspond to command frames during which something notable happened in statescript to this entity. When the first delta occurs on command frame 100, we immediately create a packet and send it down to this particular client. Some time passes, and on frame 103, another delta occurs on this entity. Since the earlier packet is still assumed to be in flight, there's no reason to send down that information again, so we create a packet containing just the changes from 103 and send it down. Over here at frame 106, the server starts to realize that something is wrong, and that it probably isn't going to get an ACK for the packet sent on frame 100. At this point, the server has to decide what it resends. At the very least, it has to resend 100, but it's still too early to tell whether it will need to resend 103. In these cases, we decide to go ahead and resend the union of the two, just in case the outstanding packet containing 103 gets dropped as well. This does mean that the client might receive 103 twice, and as you can see here, it does. But the redundancy is worth it if it means it can help a client recover faster from a series of multiple dropped packets. The client knows that this is the server's behavior, and so it won't process the initial 103 packet, since not only would it lead to an illegal simulation state, that is, it would have just the changes from 103 and not 100, a simulation state that never existed on the server, but it's going to be getting a union update a bit later anyway, and that will get it up to date, so it doesn't need this first 103 packet. Finally, back on the server, we receive the ACKs from the two packets that the client did receive. Though the ACK from the first packet doesn't make the server feel any better since it knows that command frame 100 is still outstanding. The second ACK lets the server know that the client has both 100 and 103 and that at last, all is well in the world. Okay, let's switch gears and talk about the client. The local entity, if present, stores inputs and predictions as it simulates. As you may recall from before, local entities are running in the future relative to the incoming network traffic. This is so any input we send up to the server arrives before the server processes the input's command frame. Since the local entity is running in the future, it's saving off its unconfirmed activity as these predictions. When receiving a statescript packet from the server, first send an acknowledgement to the server. Ignore the packet entirely if it is redundant or out of order. As you'll recall, the previous slide showed an example of that. If the state script packet is remote, then replicate the contained data. Otherwise, since the state script packet is local, first roll back all predictions made, replicate the contained data, and then simulate back to the present using stored input. We sometimes refer to this as a roll forth. Keep in mind that new predictions are being made while rolling forth, though we use the button input and aim that we stored off the first time through. Note that this entire rollback, replicate, and roll forth process takes place instantaneously in the same frame, so it's hidden from the player. We did have to add some utilities for state script states and state script actions to help keep this process seamless. I'll be getting to those in a bit. So here we'll go over receiving a remote state script packet. In this diagram, we have a remote entity on the client receiving several state script packets from the server. It applies the updates, and that's about it. Note that in most cases, remote state script instances neither pulse links between nodes nor process events. They only tick state script states that have signed up for ticking. In this sense, they are dumb and rely on the server to tell them everything. The only exception to this is client-only subgraphs, which run a full simulation as long as the synchronized state that owns the subgraph says that they're active. Now, here we are receiving a predicted state script packet. Here's a diagram showing a local entity on the client making predictions and receiving state script packets in return. The gray bars here indicate that a button is held, and the gray dotted lines are the client sending this input back to the server. Sorry, sending this input to the server. You'll see that the client predicts some activity at command frame 100 in response to the button press, and the server experiences the same activity on the same command frame, and then sends a state script packet back down. Something similar happens at 103. At 105, the client receives a packet describing the activity back at frame 100. So it rolls back the predictions it made at 103 and 100, represented in magenta, discards them, replicates the server's version of frame 100 in cyan, then resimulates from 101 to 105, repredicting 103 in the process. Note that the ICF here stands for internal command frame. This is the frame that the state script system is currently simulating. Finally, we get something similar on command frame 108, when the client hears about the second activity from the server. So now we'll be receiving a mispredicted state script packet. In this case, something happens to the client that it didn't predict, so there's nothing to roll back. This can happen due to external causes, such as being stunned or dying. Then at frame 103, the client predicts that it performed some activity, but the server does not. Perhaps yet another external cause prevented the activity on the server. Once the client realizes that it won't receive a confirmation for its prediction on frame 103, it rolls it back, then resimulates from 104 to the present. So let's go back and see how all this applies to Reaper's new secondary fire ability. Hold secondary fire, wait, go to third person, let go, and jump. I will now direct your attention to the vertical bar on the right side of the screen. This is the timeline for the state script debugger. I'm going to pause data collection and scrub back in time to see what happened. In the upper left of the screen, you'll see that it says View Server to indicate that this is what happened on the server. We're now going to go step by step through the frame when I release the secondary fire button. You'll see the down subgraph turn off, including the camera 3P state. Then you'll see this bool condition checking ready to launch. It's true, so then we execute this movement mod action that will launch us into the air, and finally we set ready to launch back to false. So now let's see what happened on the client. Here I switched the view to View Client, as you can see in the upper left. First, we step through the predicted simulation of the launch. You can see it in green here on the timeline. If you look next to the cursor on the timeline, you'll see CF and ICF. CF stands for command frame. This is the frame that the Reaper entity as a whole is currently simulating. ICF stands for internal command frame, and this is the frame that the state script system is currently simulating. For now, since we've executed a predicted simulation, those two values are the same. But then watch what happens when we advance a few command frames further. The cursor is now entering this magenta region. This means that we've received a state script packet from the server and are now performing a rollback. If you'll notice, the internal command frame is now on the frame when we first made our prediction. After the rollback is complete, we're effectively at the beginning of this earlier command frame. Next, we will enter this cyan region, and then replication begins. Note that replication doesn't involve following links. To conserve bandwidth, it does the bare minimum. It sets the variables and then updates the states. If you're wondering why these actions aren't replicated, it's because both the setvar and movement mod action would be redundant if replicated. The setvar because variables are already replicated, and the movement mod action because the movement system performs its own replication. I'll explain more about these optimizations in a bit. At this point, we need to simulate back to the present. We need to perform the roll forth, but since there's no work to be done, the debugger doesn't record anything, which is why it appears to be missing here. But sure enough, we're back in the present now, as you can see by the command frame and the internal command frame being the same. So, doesn't all this roll back and forth make writing new node types more difficult for programmers? After all, you don't want to restart an animation or double play a sound or spawn an extra particle system just because you receive a packet from the server. The answer is yes, it is harder, and while StateScript largely succeeds in shielding scripters from networking details, C++ programmers will occasionally have to grapple with these kinds of problems. To help out, states have various utilities, such as a reason enum for every state activation and deactivation. Reasons could include things like link traversal, rollback, replication, the entity being destroyed, etc. States also provide functions for learning about the current phase of the simulation, including access to a summary of all activations and deactivations for a state on a given frame. Then we have onBecameActive this tick and onBecameInactive this tick, which the client sync manager will call on your state at the very end of a frame if your state's activation status differs from the beginning of the frame. This is useful if your state just deals with output, such as producing visuals, sound, or UI, and doesn't need to feed back into the StateScript simulation itself. If that's the case, don't worry about implementing onActivate or onDeactivate. Just wait until the end of the frame to react. This helps avoid pops and extra effects caused by a state turning off and back on during a rollback rollforth scenario. Finally, we have putUpdate and getUpdate for transmitting a state's data from server to client. While useful, these two functions can be a bit tedious and error-prone, so we can do better. More on that in a minute. So actions also have some utilities, such as a separate doRollback call that is invoked during rollback, as well as access to temporary rollback storage. This storage is needed since actions are singleton objects with no storage of their own, yet we want a bit of state so that we can prevent things like a sound playing for a second time during a replication or rollforth. This violation of the whole actions have no state rule is admittedly not ideal, but it seemed like a worthwhile concession. And fortunately, we don't actually write these sorts of predictable actions very often. So even with these utilities, we still found it a bit difficult to write synchronized states. So we came up with another idea. Instead of putUpdate and getUpdate, use structured data-based mirrored data that automatically replicates from server to client and automatically handles rollback. With this, programmers no longer need to transmit their state's data manually, reducing implementation time and cutting down on bugs. Even better, programmers don't need to write custom logic for handling their state's internal data being rolled back. Let's look at another demo of rollback and rollforth when firing Tracer's pistols. Here we see the weapon volley state emitting each shot as we simulate our local prediction. So here we start rolling back, since we received a packet from the server. The cyan here is replication, coming up next. There it is, giving us the server's view of things. Finally, here we re-simulate back to the present. Notice how the weapon volley state, though it's dutifully ticking on each internal command frame all the way back to the present, is not emitting shots that it already emitted. That's because projectiles whose simulation and synchronization are handled by an external system aren't rolled back the same way that StateScript states are, and the weapon volley state here needs to be aware of that. So while StateScript provides utilities and features to help states reason about these sorts of rollback, rollforth scenarios, it's still up to the individual states to do the right thing. Finally, when resimulating or rolling forth back to the present, it's important to know which pieces of data are historically accurate for each command frame being processed. For historically accurate data, we have all variables and states on the local entity, which makes sense. That's what we're currently simulating after all. We have button input and aim, and we have the positions and poses for all entities. This is especially important for abilities since abilities often succeed or fail based on the relative positions of entities. It's worth noting that the server also has historical data for positions and poses, and it knows our round trip time. So during its simulation, it's able to access the exact same values for position and posing as the client. Tracking this historical data on server and client is vital for avoiding mispredictions. And then for things which have no historical data, we have variables and states on remote entities, data from other entity components, such as for health and filtering. Sorry. So as it turns out, it's actually okay that we're only accessing the latest and greatest version of this data, since unlike positions and poses, the server was never rewinding it on our behalf anyway. Put another way, accessing historical versions of this data during resimulation would actually make us more likely to mispredict. Okay, so let's see how we're doing. First, we have usability. Sure enough, Scripters don't have to worry about networking details. We have responsiveness. We predict ahead so weapons and abilities respond immediately to your input, then roll back to incorporate updates from the server. We have security. The only data we send to the server is button input and aim, so hacking the authoritative server state is impossible. We have seamlessness. The core system and sync manager provide various features to help engineers implement seamless rollback, replication, and roll forth, all in the same frame. That just leaves efficiency, which we've covered partly with our discussion of state script deltas, ghosts, and packets, but there's still a bit more to talk about. So for a quick overview, the state script delta ghost packet paradigm allows for tolerance of and recovery from dropped packets without resending every intermediate packet. If you'll recall, this is due to how unions are used to encompass multiple deltas at once. To keep bandwidth consumption as low as possible, StateScript analyzes scripts during their compilation to discover synchronization requirements. For local entities, StateScript packets must contain everything so prediction can be accurate. StateScript packets can't omit anything when sending data to a client regarding that client's local entity because, presumably, everything that's in the script is required for accurate simulation. In reality, there's probably a bit more we could do with figuring out which states, variables, and actions only have effects on the server. But writing an algorithm to prove that at compile time would be a bit tricky, and optimizing for the remote case was more important to us because, at least for heroes, there's only one local hero and 11 remote ones. Still, it's something to consider for the future. For remote entities, this is where we see some real bandwidth optimization opportunities. Remote entities do not simulate their synchronized StateScript instances. They might still tick active states that have signed up for ticking, but they won't pulse links in the synchronized portions of their scripts. StateScript packets only need to include states and actions that remote instances care about, and variables referenced by those states and actions. So how does StateScript know what needs to be synced? Well, to indicate that a particular state or action is needed by remote instances, we add an attribute to the structured data for our node type. As you can see here, it's sync all. With the attribute, states and actions will be synchronized from server to client unless they specifically opt out of remote syncing at runtime. Sometimes they can opt out if, for example, they know that the variable they need to, the variable they modify isn't needed yet by remote clients. Without the attribute, states are only transmitted to local clients, and actions aren't transmitted at all. So let's talk about compiling. During the compilation of each StateScript graph asset, we use reflection to determine which nodes need to be sent to remote clients. We then analyze each of these nodes to see what variables they reference. These variables go into a list of variables that could potentially be synced remotely. We then determine how many bits are needed to reference these nodes and variables during the creation of the StateScript payload. This effectively gives us a unique optimized message protocol per script asset that we can use for synchronization. We're able to do this because the server and client share the same assets. So let's see how these optimizations play out. First, we'll watch this remote tracer fire her pistols in the server view. You'll see a whole lot of nodes lighting up since the server is simulating everything. In the upper right, you'll see the variables that this instance is using. For the sake of this demo, I'm hiding the owner variables to make it easier to see the before and after. So now let's switch to the client view. So notice how few nodes are lighting up now and how short the instance variable list is. Not only is this a significant bandwidth reduction, but it's a win for client performance as well since there are fewer nodes to execute. We'll switch back and forth once more so you can see the difference. That's server. And that's client. For those of you wondering about numbers, here are the local and remote bit counts for tracer firing a full clip and reloading, which takes about 2 seconds. If you'll recall, we've optimized for the remote case, since a client has many more remote entities and only one local entity. So adding up the numbers, if you were to have 12 tracers, including the local player, all holding down primary fire, StateScript would cost about 5.4 kilobits per second. So that's the 43 and 52 seconds, 43 minutes, 52 seconds whirlwind tour of StateScript and how we networked it. So let's talk about some of the benefits we've enjoyed because of it. So first, we have rapid iteration. We've ended up with a flexible, iterative workflow for designers in which new heroes can quickly be taken from prototype to shippable with little to no new code. This is sort of hard to quantify, but I have a chart here to show the new node types we needed for each hero we developed. This is in chronological order of development. And by the way, this is by no means a complete list. It's basically what I was able to think of as I typed it out. So as you can see, the first several heroes needed a whole bunch of new node types. This makes sense, of course, since we hadn't built up a library of node types yet. But as we went, heroes tended to require fewer and fewer new node types to implement. Several of the later heroes didn't require any new node types. Of course, there are always bugs to fix, new gameplay features to add to existing nodes, so our gameplay engineers won't be out of a job anytime soon. But having this collection of building blocks has definitely unlocked the potential of our designers to iterate quickly on behavior. So, automatic syncing and state machines. When new gameplay features are required from engineers, they can generally be added without the need to write synchronization or state machine logic in code. As it turns out, the majority of new node types either only have a server implementation or only have a client implementation. Now, it's possible that a client node might consume variables or other data that come from the server, and it's possible that a server node outputs variables and data that are destined for the client. But it's not often that we'll actually need to synchronize node data by hand. As for state machines, every once in a while we'll have a heavy-duty StateScript state that runs its own internal C++ state machine, but that's the exception. For the most part, StateScript is our state machine. Fewer lifetime and desync bugs. Certain types of bugs are less common, including lifetime issues and server-client desyncs. This is one of those claims that I'm sure will come back to haunt me as soon as I make it. But we've had relatively few bugs where something stays on that should have turned off or exists on the server but not on the client. We did our state machine and synchronization logic in one place and then hammered on it for years to get it right. And because we did, there's an entire category of bugs that we just don't see as often. Now that I've said that, please never visit our subreddit again. Just kidding, we love you, Reddit. So now let's talk about some of the challenges with our approach. First, there is a hefty upfront implementation cost for the runtime, an editor, and a debugger. This took a whole lot of work to make. From the time Overwatch spun up in late 2013 through today, I've personally spent about half my time developing the StateScript runtime, the sync manager, the compiler, the debugger, and various core features. Then we have the countless node types that gameplay engine and server programmers have been making all this time. And for our editor, we also get several man-months a year of tools engineer support. So it's a big undertaking. Then, there is a learning curve for engineers, particularly when deciding which parts of a feature belong in code versus script. We have many, many different systems in Overwatch, and when a new complex feature is needed in that system that also needs to be configured by StateScript, it's tempting to just make a single node in StateScript that drives the entire feature. Sometimes, however, a feature is complex enough that you'll want to break it into multiple StateScript nodes so that parts of it can be reused or activated at different times. If the feature itself involves a state machine, there's a good chance that you'll want the state machine to be implemented in script rather than C++. After all, that's exactly what StateScript is designed to handle. However, and I've been guilty of this myself, this can be taken too far. Sometimes you really do just need a single node. Any more, and you're just adding complexity and surface area to a relatively simple task. So there's a balance to be struck, and it takes time to figure it out. There can also be a bit of a learning curve for engineers and designers to adjust to the declarative style of scripting that most of our scripts use. While powerful, declarative logic is different from the more imperative style that most developers practice on a daily basis. So that transition can take a bit of time and effort. And then there's the occasional workaround. The eventual consistency networking model does not provide a perfect blow-by-blow replication, meaning the occasional workaround is required in scripts to achieve the correct result. This is an unfortunate consequence of having a state-based rather than an event-based replication scheme. Simply put, we don't have the bandwidth to give the client all the intermediate steps of what happened on the server. Instead, we send down the variables as they were at the end of the frame, followed by the states and actions. Here's an example of where the order matters. Symmetra's secondary fire involves her charging up a shot and releasing it when the button is released. The longer she charges, the more powerful the shot. When we fire the shot, we immediately set the scalar variable back to 0. This works fine for the server, but when remote clients go to replicate this, all the projectiles show up with a size corresponding to a scalar of 0. This is because we replicate the scalar variable first, followed by the weapon volley state. Fortunately, this is easy enough to fix. All we need is a second variable that stores the visual scalar to be used by the weapon volley state on the client. Still, it's counterintuitive and more than a little unnerving that these kinds of idiosyncrasies exist. Luckily, I can probably count on one hand the number of times this issue has actually come up. So it's not exactly a deal breaker, it's just mildly annoying. So, considering all of those challenges, is making an automatically synchronized state-based scripting system a good idea for a AAA game? Well, we believe so. Declarative scripting seems to fit nicely with our eventually consistent networking paradigm. We were able to make it performant and bandwidth efficient enough for production, and our team has become proficient enough with it to churn out lots of cool content. If we had to do it all over again, we'd probably end up with something very similar. So, Q&A.
I was wondering if you could provide an example of one of the cases that you found it was better to do a behavior through code than the scripting.
Usually we prefer to do things through code when either they involve complex loops, because you can express loops in script, but it's a little bit messy and you have links sort of going back and forth on top of each other, or when there's a performance consideration. Raycasting is probably the best example of something where you don't want to try to do that in script. So instead you would have a raycast state that, or an action, either a raycast action if you just want it to be fire and forget, or a raycast state that will actually tick and give you a result every frame. But all of the actual heavy lifting of the raycast is done in C++.
Okay, thank you.
Hi. Are state scripts binary assets? Do you have any affordances to help, say, merging if multiple people are working in similar areas, to help resolve issues with dependencies, and to help with things like reviewing changes or even just coming back after a time and understanding what a state script even does?
So all the state script assets are exclusive checkout, so only one person can actually be making changes that they're going to commit. We actually have also a notion of local checkout, which is sort of like a way to do stuff even though you're not intending to check it in. So you can still work, but we only have one exclusive checkout on an asset in our asset system at a time. So that, what you point out, has been a problem in the past, where we'll actually have multiple people who need to change a script. So the solution in general, what we found, is to actually break your scripts into multiple smaller scripts. It's not a perfect solution, but it does mitigate that problem to some extent. So it's something we're aware of.
Do you run into dependency issues where somebody's modifying a script that I take a dependency on, but their change conflicts with what I'm doing in mine?
That doesn't happen all that often, because usually if you're making a change, you will be in communication with people who are working in adjacent areas. So that particular problem doesn't come up as much.
Thank you.
So actually working on multiplayer game and recently switched to a state-based system for our gameplay logic, and was kind of curious, how early on in development did y'all decide to go with a state system for a lot of y'all's gameplay?
So we had been developing with some form of state script since 2011. So it was before Overwatch began, back on Titan. We were also using state script. I think we had done some prototypes early on, and we had concluded that writing synchronized state machines by hand was awful. And so we really wanted something that let us just do it automatically. And so Paul Keat and I, Paul's another developer at Blizzard, we sort of came up with this idea of having a sort of state machine system, in this case state script, and I worked on sort of the synchronized aspect of it. Oh, yeah, sorry, left side.
When you came up with the idea of going with this whole scripting solution, was there a lot of pushback on the engineering side for kind of developing this whole soft-coded solution, or was everyone pretty agreeable that that was the right direction to go, and how did that discussion kind of play out?
In short, yes. There was a bit of a period of trying to win people over, but eventually, and also thanks to the courage of my lead, Tim Ford, who I don't know if he's actually here or not. There he is in the back. So he courageously stood up for me and let everyone know, like, no, this is really a good idea, and we eventually got our way, and were able to develop the system.
Cool, thanks.
How expensive is client rollback, I guess, both in processing and in development time for each state? And why not just like save off the last server update and restore it? So
the fear, to answer the second part first, the fear of actually storing off state was that you would basically be storing off a very large amount of state, and it would take time to actually serialize that out or copy it out or whatever the method was, because every single state is sort of its own class, and so it would have to implement that, or we'd have to use mirrored data, and basically the fear is that that would actually be really slow. So what we end up doing instead is the way the predictions are stored is just sort of like it's basically saying, hey, here's the previous value of a variable or previous value of a state. And it actually is probably faster just to roll back over that sort of list that we've accumulated than it would be to try to find like the full state and just smash it in with a big mem copy or something. So it's worth considering, I guess, the other way, but it really did seem like the fastest way was just make a list of what changed and then run it backwards. And then to answer the first part, actually, can you repeat the first part of the question again?
How hard is it to do the rollback on the client?
So it is actually expensive. It's probably roughly expensive as simulating forward. Luckily, you're only doing it for the one local entity. So you don't have to do any of this for remote entities, and all of that is probably going to be the bulk of your simulation is the remote entities, getting them, deserializing and processing them.
And is that a lot of extra code to handle it?
It's one file, 2,000 lines, I don't know. It's code. I don't know if it's a lot. Sorry, I'm going left, right. Left.
In an early slide, you had a figure that looked like you could group off a group of nodes and designate them as being client-only or server-only?
Yes.
Is that correct?
Yes.
Okay, so that seems to run contrary to your goal of not having script authors to understand, essentially, the underlying replication mechanics. Can you just...
Yeah, so it is one of those things where that's our goal, but you don't always 100% reach your goal. Sometimes you do need those, in particular when you're doing a lot of mixing of UI, where you need to know about who's local to me, am I the local player? When you're dealing a lot with, UI, you tend to use client-only subgraphs for that, just because you can reason about the local player, which is something the server can't do. So you can actually store the local player in a variable or store the team index you're interested in a variable, that kind of thing. We basically use a mix of that, but it's the sort of thing where you're opting into it when you're writing the script. Like this just needs to be on the client, so I'm going to write this client-only subgraph for that. But it's the majority of our scripting is still not in one of those subgraphs. So you still save a lot of time by not having to do that. The server-only subgraphs were mostly added as optimizations when we really didn't want the client to predict this stuff because it involved extra ticking or extra stuff like that.
Do you ever have a graph that would have a server-only component and a client-only component, or is it typically just...
It has definitely happened, yes.
Okay, thank you.
All right, right side.
How portable is this solution if you were to start a new project, maybe with a whole new engine?
So StateScript is very dependent on both our asset system and our networking layer and structured data, which is part of our asset system. So right now, it wouldn't be very portable. I think you could write a version of it which was more generic. We just haven't done that yet.
Hello, I'm Christian. How much the percentage about the logicals are implemented by this script?
I'm sorry, one more time?
Sorry. I'm curious that how much the percentage of the logicals of the game is implemented by this script language?
I'm sorry, I'm having trouble understanding.
What percentage is native code versus script?
Okay. That's a little bit hard to measure, I guess. So when we make a new hero, it's almost entirely in script. We only add native code for new states, new nodes, that kind of thing. Obviously, there's still a lot of code. Once you get outside of the game simulation, there's still plenty of code that needs to be written for rendering and networking and server-side stuff.
Okay, thank you.
First off, thank you for the talk.
Sure.
Second off, from the Overwatch network talks around last year, it was mentioned of favoring the awesome moments for the player. How did that tie in with the rollbacks and pre-simulation for the player? Was it something you defined on a per instance basis? Or?
The awesomeness?
Yeah, when I think it was certain abilities would get prioritized even though the client can't be trusted, that aspect, was that tied in here?
So if I think I understand what you're saying, there are certain abilities that will prevent rewinding. So, and by rewinding, I mean, let's say someone tries to shoot at you, and you use Wraith form as Reaper, you'll basically sort of not take damage even though they think they hit you, and even though we would normally rewind Reaper to that frame of reference of the shooter, well, we're not going to honor that because there are times when you want to mitigate that. and allow the defender, the person being shot at, to sort of escape. And so we actually have a node in StateScript which we can drop to say block rewinding. Don't allow any rewinding because at this point I have used my escape move.
Thank you.
Can you talk a little bit about the debugging tools you have for StateScript? And also, can you kind of, when a bug happens, simulate the game and step through the script?
Yes, the debugger stores a history of everything that's happening on every entity. It was all just written in C++. There were no external tools used. I just wrote it. But yeah, it'll actually record everything every entity's doing. And then yes, to figure out bugs, to catch bugs and debug them, you can jump to the entity that exhibited the bug and then sort of step through the history. And you can switch between server and client. Does that answer your question?
Yeah, very cool.
Okay. All right. Well, if that's it, make sure to stay tuned for David Clyde's excellent talk coming up next on the data build pipeline of Overwatch. And if you have any additional questions, just feel free to hit me up and we can take it out there.